All right, so last time we talked about this conversion formula. Whenever your mean and your standard deviation are not equal to 0 and 1 respectively, then you're going to have to use this conversion formula. So with this conversion formula, once your mean is 0 and your standard deviation is 1, that's when we can go back and use table A2. Table A2, which are your z-score tables. So it's very important for us to know that the mean is 0 and the standard deviation is 1 before we use those tables. If your mean and your standard deviation are something other than 0 and 1, then you can't use those tables. You have to use this conversion formula first. So this is where we left off. I looked at this example, and we finished that one, and I didn't get a new one started just because we didn't have enough time. All right, so then today we're going to go ahead and talk about this conversion formula a little further. All right, so let's go ahead and look at the next example. So we finished example 1 in your notes, and the next slide that was on here was just a warning, and it was just a warning about not confusing z-scores and areas. So the z-scores are that's the horizontal column that's to the left of your table. And so what I'm going to do is I'm going to show you one more time where I got those tables. So right now your screen is changing. Okay. So there have been questions about where I ended up getting those tables from. And so remember that when you go to My Stat Lab, you are going to go over to Chapter Contents towards the bottom. That's your ebook. And when you click on that, you have to go to Tables, Formulas, and P-Values. That's one place you can go. And that's what I clicked. And then what comes up are those tables, and I would suggest that you print them out. For the midterm, I will provide you with a clean set of tables. But for your own copy, for doing the homework, you should copy these, because sometimes this ebook doesn't come up right away. Okay, so that's where we ended up getting these tables. All right, so for today's lecture assignment, the questions that you have to do for the lecture assignment, one of the questions I asked you was when it's okay to use this table. The only time it's okay to use this table is if the mean is 0 and the standard deviation is equal to 1. If the mean is 0 and the standard deviation is equal to 1 and you're working with the normal distribution, then you can use this table. But it's only for the case where you have the mean is equal to 0 and the standard deviation equal to 1. That's the only time you can use this table. And if the mean is not 0 and the standard deviation is not 1, you have to use that conversion formula to standardize your distribution, to standardize your values. All right, so that is the condition for this table, to use this table. And there's two sides of it. One has a negative z-scores, the other one has a positive z-scores. So we're going to continue using this table today. When you look at the table, the body of the table, that's where your areas are. And the leftmost column, that was your z-score. So don't confuse the two. Just remember what we did last time. Okay, and again, when I talk about the body, I'm talking about this part of the table. Right, the middle, that's your body. That part of the table is your body. And then the outermost column, those are your z-scores. So these are our z-scores. That's the outermost column. That's up to the 10th place, and then the first row has the 100th place. So your z-scores are in the leftmost column with the 100th place in the first row. And the body of your table has your areas. So remember, areas are in the body of the table. Okay, so I am going to go over the transformation formula, but notice it's written a little differently this time. All right, so let me go ahead and remind you about what that formula looked like before, when I first started talking about this. All right, so we had Z equal to X minus the mean divided by the standard deviation. And so when we use this transformation formula, we were able to get a Z, and then we looked that Z up in our tables, and then we got an area which was the same thing as a probability. So for this part of a section that we're looking at, we're now interested in finding X. So you're going to use this transformation formula, and all you have to do is solve for X. That's how I ended up getting what you see here. Okay, so if you're trying to solve for X, then you simply have to multiply both sides by sigma. So you're going to have Z times sigma, and that's equal to X minus mu. You're trying to solve for X, so you're going to add mu to both sides. So you're going to get mu plus Z times sigma, and that's equal to X. This is the formula that's going to allow us to find X. And that's the same formula that I have typed out on the side. But it just comes from your transformation formula. All right, it comes from your transformation formula. So you take the mean, and you add Z times the standard deviation. So to the mean, you add Z times the standard deviation. So these two are the same formula. And again, it comes from that transformation formula we talked about the other day. So why is it written in a different way here? What we're going to do is we should also be able to work backwards. So it's not only important that we're able to find the probability like we were in this example. We were asked to find the probability. And when we're asked to find the probability and the mean is something other than 0 and the standard deviation is something other than 1, then we would have to use that formula I just talked about. All right, so if you're asked to find the probability but the mean is not 0 and the standard deviation is not 1, then you start using this transformation formula. If you're asked the question in a different way, and I am trying to find that out. Let's see if I can go back to that slide. Okay, there it is. In this case, we're given an area and we're trying to find the z-score. Okay, so in this case, it says use the data from the previous example, and this is example number 1 that we talked about. So I'm going to go back and get the information from example 1, and that information was the mean and the standard deviation. So I'm going to use the same mean and the same standard deviation. So let me write it up here. So the mean was 172 and the standard deviation is 29. So I'm just using the same mean and standard deviation for example 2. So 172 and 29. All right, so using the data from the previous example, we're going to use this to determine what weight separates the lightest 99.5% from the heaviest 0.5%. So the way the question is phrased, it's not asking you for a probability. You're not asked to find a probability. Instead, you're given a percentage. and you're asked to find the value that separates one part of the graph from the other. So anytime you're given a percentage, that is the same thing as giving you an area. And an area is the same thing as a probability. So the area is the same thing as a probability. If you're given a percent, you're given an area, and that's what we're given here. You have to turn that percent into a decimal. So 0.9950, I'm just purposely making sure that I have 4 places after the decimal, because in your table we have 4 places. And so when you look at our graph here, that is the area to the left. The heaviest 0.5%, that's located on the right of your graph. So the graph goes from left to right, where the right is the larger numbers, just like a number line. From left to right, and the right are the larger numbers. So I'm trying to find this value of x. What is x equal to? What is that weight that separates the lightest 99.5% from the heaviest 0.5%? All right, so the mean is not 0 and the standard deviation is not 1. So I have to use that conversion formula, but I have to use the form of the conversion formula that's solved for x. Okay, so you remember that we had z equals x minus mu divided by sigma. That was our conversion formula. But in this case, it asks us to find the value or the weight that separates one side of our graph from the other. So since we're not looking for probability, we have to use the formula that starts with the x. So x equals the mean plus z times the standard deviation. Okay, so that is the alternate form of that conversion formula we have to use. And you're always going to use that when it asks you to find a value that separates one part of your graph from the other part. Okay, we know quite a bit from this. We have a mean, we have a standard deviation, so I'm going to start there. So x equals the mean, which is 172. I do not know the z-score, but I do know the standard deviation, and that's 29. So it looks like my unknown here is that z-score. So I have to figure out what that z-score is. Okay, so I go from my normal distribution to my standard normal distribution. So right below my curve there, I am going to put a horizontal axis on there, and I'm going to label this as z. Okay, so these are my z's. That would represent my standard normal distribution. Now in a standard normal distribution, what is the mean? What is the mean for standard normal distribution? Does anybody remember? Okay, so I put a 0 there. That is the mean. I am going to now, using the area that I'm given, I'm going to look up that area so I can get the corresponding z-score. And then I'm going to write it right here. That question mark is going to be the corresponding z-score for when the area to the left is 0.995. So we're given area, we go to our table to find the corresponding z-score. Now, I have to think about this graph, whether is my z-score going to be positive or negative. So here's the mean, and the z-score I'm trying to look for is located on the right side, not on the left side. So that should give you an idea of whether the z-score you're looking for is positive or negative. The z-score is to the right of the mean, and the mean is 0. So then the z-score you're looking for would have to be positive because it's to the right of 0. All right, so let's go to the tables, and remember the area to the left, that's what I'm looking up, is 0.9950. That is the area to the left. So I have to look at my positive z-score. So I have to look up 0.995, I think it was, 0.995. All right, so I want you to look at that table, and you have your table, and I want you to tell me what corresponds to an area of 0.995. What corresponds to an area of 0.995? Again, the area that we're given is 0.995. So what z-score corresponds to that area? Okay, good. So you see that you're working from the body of your table, right? You're working from the body of the table. So the body of your table are all these right there. Okay, I didn't mean to make it that red. So this is the body of your table. I'll delete that because we don't need it to be that red. All right, that's part of the body of your table. All right, so the area, so there's a question about why that z-score is outside. Notice that 0.995 is right in between two given areas. So 0.995 is right in between 0.9949 and 0.9951. So the value we're looking for is right in between two given values. Whenever that happens, you do something that's called interpolation, and so you get the corresponding z-scores. So you look up 0.9949 and you get its z-score, which is 2.5. And then you get the z 2.5, and then what is the top number at the top? If you guys go up here, what is that top number? Let's see, this was 0.00, 0.01, 0.02, 0.03. Do you know where I'm looking at? 0.04, 0.05, 0.06, 0.07, right? Okay, so that area of 0.9949 corresponds to the z-score of 2.57. And then the other area is 0.9951, so that z-score is 2.5, whatever this one is here, 0.08. So that z-score is 2.58. So whenever we have an area and that area is exactly in between the two given areas, then you take the z-score for the first area. You take the z-score for the first area, which is 2.57, and then the z-score for the second area, which is 2.58. You average that out. So you add it together and divide by 2. So when you do that, tell me what z-score you get. All right, so you all see how we get the 2.575. Okay, so the table kind of keeps track of at least 2 of those z-scores, and so this is the one where you keep it to 3 places, right? You keep it to 3 places. So that's where we get the 2.575. So you notice on your table that there are 2 asterisks there, and those are very special z-scores, and that's why the table gives them to you. Those are the only ones you're going to round to 3 places. But just curious about where that number came from, that was just my explanation right now. That's how the table came up with that z-score. So yes, for this example, the z-score that corresponds to the area of 0.995, which isn't on our table, but it's right in between 2 given areas, is 2.575. So you follow the arrow. All right, so that is my z-score. So I'm going to take away my question mark. We don't need that question mark anymore. And I am going to put in there 2.575. That's my z-score. So when I go back to the formula, I know what to write there. It's x equals 172 plus 2.575 times 29. Now that you know your z-score, you can plug it into your formula and you know what value of x you have. So that value of x is going to be what separates the lightest 99.5% from the heaviest 0.5%. So when the question is asking you for a value that separates one part of your graph from the other, then you're going to be using this formula. You're going to be using this transformation formula. All right, so we're going to round this. I mean, x represents weight, so you can go ahead and round it to the 10th place. That would be fine. I didn't give you any rule there. So what are you getting? If you round to the 10th place, what are you getting for the weight? So I have a few in agreement. Okay, great. All right, so you guys agree that it's 246.7, and we're talking about pounds here, right? 246.7 pounds. So that is the weight that separates the lightest 99.5% from the heaviest 0.5%. So, and you could write pounds, yeah. You don't have to, but know that the x here is a continuous random variable. So that means a continuous random variable comes from some type of measurement, and pounds or weight here is a measurement. That's our horizontal scale. I'm just curious. I have office mates on both sides, and this is the time where we're transitioning classes. So I keep hearing doors close and open and close and open. I'm just wondering, do you hear that? Okay, so I have a very good microphone here because it's a headset. Okay, because it is loud. As they come in and out, it is loud. Okay, I'm glad you can hear that. All right, so that's this part. Okay, so let's go ahead and move to a different example. Oh, actually, in my solution, I just kept it to, I rounded it to 247, but for the midterm, I will be giving you instructions, of course, how to round. Make sure when you're doing the homework that you are reading the instructions as well. Okay, so that was the end of that part of Chapter 6, Section 6.3. So let me just go ahead and do just a quick summary here of what we've done. All right, so what I started off doing is last lecture we talked about how Table A2 works. All right, so we talked about how Table A2 works. And so let me just make sure that I've covered everything I wanted to cover. When you look at the homework, the questions in today's lecture assignment that I give you. All right, so we talked about Table A2. And Table A2 can only be used when the mean is equal to 0 and the standard deviation is equal to 1. That's when Table A2 can be used. So it's only for standard normal distributions. That is the restriction. it can't be any normal distribution. It has to be a standard normal distribution. I also showed you how that there are commands on the calculator. We went over the second, so on the calculator, I showed you a command, and that command was the second inverse command. It was inverse norm. It was second inverse norm, and then you enter the area to the left. When you do that, that gives you a z-score, and that's okay to use. So this one gives you a z-score. That one's okay to use. However, I also told you that there was another command, and it's called the normal CDF. Now, the normal CDF command replaces what we do with the table. So if you use the normal CDF command and you just enter your left z-score and your right z-score, you will get the area under the curve. You'll get the probability. And the warning that I have for you is that that will not always match what we find on the table. So on your homework, you need to make sure you're working with the table so you don't get any questions wrong. Now the table, they are only rounded values. But when you use your calculator, it actually is more exact. It's exact because it takes it a few places more. But the two do not match. So the normal CDF command will not always give you the same probability as when you're using table A2. They will not always match. So that for that reason, I told you to use your table. That's how the homework program grades is based on the table. All right, so when it comes to the midterm, on the midterm, you want to make sure that you're using table A2. Do not use the normal CDF command. When it comes to the midterm, you will have to show your work. Okay, so I do not want you using that second normal CDF command. You will have to show your work and use table A2. Okay, so I'm looking through it, and I think I've gotten almost everything there. One other thing. Also, when you're working with continuous distributions, Chapter 6, that was what Chapter 6 was all about. Chapter 6 was all about, and we're not done with it yet, so Chapter 6, we have continuous distributions. And so all continuous distributions, when you're trying to find a probability, probabilities are found by using the area underneath the curve. So for continuous distributions, whether it's the standard normal distribution or the uniform distribution, that's the one that looked like a rectangle. It had a rectangular shape. So no matter which continuous distribution you're looking at, the area underneath the curve was the same thing as a probability. So that was the concept in all this Chapter 6 that we've been doing. So the area underneath the curve for continuous distributions is the same thing as a probability. Or the probability is found by finding the area underneath the curve. Okay, so that's what we've been looking at so far. All right, so let's go ahead and, I was just curious if there are any questions. So I'm going to just stop for a minute and see if there are any questions so far. Okay, so I see my first question here. So the question says, do we need to memorize all the formulas for the midterm? No, you do not need to memorize these formulas. Remember that you do get to bring in a list of your formulas. All right, so to see the specifics on that, you want to make sure that you are reading the discussion board. All right, but you are able to bring in a list of your formulas that we've been doing. So no need to memorize. Okay, so we are now going to go into something called sampling distributions and estimators. So the main objective in this section is to understand the concept of a sampling distribution of a statistic. Now the sampling distribution, this is a distribution of all values. This distribution is a distribution of all values of that statistic when all possible samples of the same size are taken from the same population. So a sampling distribution, let me underline that, a sampling distribution of a statistic, and remember a statistic is like X bar and S, the mean, the standard deviation. Measurements from a sample is a statistic. So sampling distributions is a distribution of all values of that statistic. Again, a statistic is a measurement from a sample. And this occurs when all possible samples of the same size are taken from the same population. So we will see that some statistics are better than others for estimating population parameters. So a parameter is a measurement from the population. A statistic is a measurement from a sample. So some measurements from the sample are better than others for estimating what's happening in your population. And we're going to see which ones are better. Okay, so the sampling distribution of a statistic, and a statistic is a measurement of what's happening in a sample, such as X bar, which is your sample mean, and a sample proportion, which is P hat. We haven't talked about that, but that's the notation for a sample proportion, P hat. It's usually a percentage, or a fraction, or a decimal. So that proportion can look like a percentage, a fraction, or a decimal. So a sampling distribution of a statistic, which could be X bar or P hat, is a distribution of all values of the statistic when all possible samples of the same size N are taken from the same population. So you're grabbing a group of items from one population. So you go and you randomly select a group of the same size from that population, and you continue doing that. And what we do is we look at the distribution. So for every sample that you select, you're going to be noticing what the sample mean is for each sample. And then you're going to look to see how that's distributed. What is the behavior? If you keep track of all the means from every sample you take from your population, what does that look like? Now the sampling distribution of a proportion is a distribution of sample proportions, and proportion could be a fraction, a percentage, a decimal. And this is the case with all samples having the same sample size and taken from the same population. So we're looking at the behavior of proportions from every sample you take from your population. We're going to also see what behavior is happening there. Now we see that sample proportions tend to target the value of the population proportion. So all possible sample proportions have a mean equal to the population proportion. So sample proportions are good estimators for what's happening in your population. And because of this, the distribution of sample proportions can be approximated by a normal distribution. Okay? All right, so basically we're just looking at the distribution of your sample statistics. All right, and here it goes on to talk about the sampling distribution of the mean. And again, what you're looking at is the distribution of all sample means from your different samples of the same size. And these are samples that are taken from your population. So then what we want to do is we want to be able to see what kind of behavior we see when you keep track of all the means from every sample that you obtain from that population. All right, now we will have sampling variability, and that's just something that happens because we have variation from sample to sample. But if you keep track of what's happening with every sample mean from every sample that you obtain from the population, you still tend to see a pattern. You're going to see what's happening with that distribution, and this just says there might be variability. But if you have enough of those groups, then you're going to have a good picture of what's happening. All right, so I'm going to try to explain everything I talked about by using a few numbers, and then there's a table here. Okay, so this is your one example that you're getting for this section, and it's just the purpose of this is to explain what sampling distributions are doing. So we have a controlled population, and this population just has the numbers 1, 2, and 5 because it's easy to work with. And what we're going to be doing is we're going to be randomly selecting samples of size 2. But we're doing this with replacement. So what I need to do is I need to find out how many samples of size 2 can be obtained from this population of 3 numbers when I'm using with replacement. All right, so using what we've done in the past, with our counting methods, if we have 2 numbers to select, because our sample size is 2, so I need to select 2 numbers, and it says with replacement, how many options do I have for the first selection? So I'm selecting 2 numbers, and the options are the numbers 1, 2, and 5. So how many options are there for the first selection? Any ideas? Okay. So you only have 3 numbers to choose from, right? 1, 2, and 5. Those are your 3 numbers. So when you go and you select, you're starting to select your sample, you have 3 options. Now it says with replacement. So when you go back and you select the next one, you still have 3 options because you're putting the first one back, right? So you go into your population and you're going to grab a sample of 2. So you go in and you grab 1 and you put it back in to grab the second one. So you always have 3 options because it says with replacement. So remember with our counting rules, to find how many possibilities that gives us, we multiply. So the possible for the first and the number possible for the second. So there's 9 ways that can happen. Now I could go ahead and list my sample space, just like I did where we had the family of 3 children, which was boy, 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 girl, 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 boy, girl, boy. We could do that, but that, you saw that takes some time. So this counting rule allowed us to find how many ways this was going to happen. So there's 9 ways in which we can select a sample of 2 from a population that has 3. So there's 9 possible samples. Now for these samples, for these 9 samples, I am going to find the mean of these 9 samples. I'm going to find the median, the range, the variance, and the standard deviation. So these are all measurements that we've found back in the early chapters. So for each of the 9 samples, we're going to find all of these measurements. And then we're going to compare those measurements with what's really happening in the population. And the population is so small that we could figure out what's actually happening in the population. All right, so we're going to compare the measurements from our samples to what's happening with the measurements in our population. Okay, so that's what this table, well, we're almost there, not exactly. So we have our population, which I talked about, 1, 2, and 5. And we're going to randomly select samples of size 2 with replacement. That gives us 9 possible samples. So we're going to find the mean, the median, the range for these samples, for these 9 samples. And then compare it to what's really happening in our population. Okay, so this is the table I was hoping to get to. All right, so the first thing I hope that you notice is that these are all the different samples that can be obtained when we have a population that has the numbers 1, 2, and 5. This is how many ways you can select a sample. This is how many samples you can select when you have with replacement and you're looking to have your sample of size 2. So your n is equal to 2 because you were selecting 2 numbers. This is how many ways that can happen. And so if you count the total ways that can happen, there's 9 of them. Okay, the next thing that was done was for every sample, the mean was calculated, which is the average. So for every sample, the average was calculated. So let's just look at this one. So how do we calculate the average? We have 2 and we have 1. So you are going to add your data values, 2 and 1, and then you're going to divide by how many of them you see. So we have 3 over 2. So the average for that is 1.5. So that's why you see the mean as 1.5. So you're going to take every sample and find the mean. And then that's the next column that you see. All right, that's this column that you see with the happy face, the one with the happy face over it. So every sample, you would calculate the mean, and then that is the column that we see. Now look at what I'm going to do. I am then going to find, let me get a different color. I am going to find the mean of all of these means. All right, so that column that I just put a box around, it looks a bit green, yellow, green. I am going to take all of those means and I'm going to find the mean of those means. It sounds strange, but I'm finding the average of all those means. So how do I find the average of all those means? So I am going to take 1, which was the mean for the first sample, 1.5, which was the mean for the second sample, 3, which was the mean for the third sample. I'm going to take all of these means, add them together, and divide by how many of them I see. So that's 1 plus 1.5 plus 3 plus 1.5 plus 2 plus 3.5 plus 3 plus 3.5 plus 5. You're going to take all of these means, add them together, and divide by 9 because we had 9 samples. So when you add all these up and divide by 9, what do you get? So add up those numbers that I put a box around and divide that by 9 and let me know what you got. Okay, so I see a lot of 2.67s. Okay, so let me write that down. All right, so when you found the mean of that column, I'm going to give that a different name. I am going to say the mean of the sample means, and I'm going to use this notation. So do you see how I'm using the mu? So at the top, I put the mean of the sample means. So the mean of the sample means, that's what you just found. And you just told me that was 2.67. All right, so what I want you to do is I want you to look at that 8/3 at the bottom of the column. Is 8/3 the same thing as 2.67? All right, so now you know what that number is. So the mean of your sample means is 2.67. The same thing you ended up with. The way that the notation, so you already know how we write that out, how we represent that. So that 2.67 is the mean of all means. Now look at, if we just take our population, look at our population. The population was 1, 2, and 5. So what if we find the mean of our population? So go ahead and find the mean of your population. So that means you're taking 5 plus 2 plus 1, and then you're dividing by how many you have there. So 5 plus 2 plus 1, and then dividing by 3, because that's how many we have. So that finds the average. .67 again? Okay, so we already said 2.67 is 8/3, right? Okay, so again you get that 2.67. So the mean of your population, which is over here at the top, the mean of your population is again 2.67. So you see what happens. The mean of the population is the same thing as the mean of your sample means. So the mean that we found by adding up all of the sample means, so the mean that we found from adding up all of the sample means was 2.67. It just happens that that is the same number you get when you find the mean of your population. So mu is the mean of my population. Mu with an x bar next to it, that's the mean of my sample means. That's the mean from all of your sample means. And they happen to be the same thing. So what we notice is if we find the average, or if we find the mean of all the sample means, it's the same thing as our mean of our population. So what we end up doing is we go into our population and we randomly select samples of the same size. And what we do is we find the mean of all of those samples that we obtain. When you look at the distribution, what we see is that the mean of the sample means is the same thing as the mean of our population. So it's very helpful to be able to obtain many samples of the same size in our population and observe what's happening with the sample means. So what happens is, the question here says, does the sample statistic target the population parameter? Yes, definitely. The mean of our sample means ends up being the same as the mean of our population. So in real life, your population is not going to end up being 3, but you kind of get the idea. You are going to have a large population, which you can't look at. It's going to be, the population is going to be too large for you to look at. But we already know that if we obtain many samples of the same size and look at the mean of all of those sample means, then you're going to target the population mean. That's what this is saying. They're going to be the same. Okay, and so then all these other measurements, you can also look at the median for all of your different samples, and then find the mean of the medians. So if you add all these up together and divide by 9, the mean of the medians is 8/3. But if you look at the median of your population, that's 2. So those don't match up. So then that sample statistic does not target the population parameter. So the mean of the medians does not equal the median of your population. So that one's not very good. And then you can do the same thing for the range. Notice that they're not the same. So the next time it happens again is when you're looking at the variance. So if you find the variance, of every sample, you find the variance of every sample, and if you then take all of your variances, add them together and divide by 9, you're finding the mean of the variances. So what we find here is that the mean of the variances is the same thing as the variance of your population. And so that's another sample statistic that targets your population parameter. And then again, that happens again with proportions. So then you see which sample statistics target the population parameter. So the sample means, the sample variances, and the sample proportions. If we take our variances from our samples and find the mean of all those variances, that is the same thing as the variance you see in your population. And again, it happens with proportions. So it's an interesting thing that happens. So we then see which parameters are better at targeting the population parameter. Let me say that again. We are able to see which sample statistics, so which measurements from your sample are better at targeting the population parameter. So what I was trying to say is exactly what I'm boxing up on here. Okay, so that is what this section is about. There are really no actual questions. I think I did ask you a couple of questions on this, on the homework, which I have not made available yet, and I will do that soon. All right, so basically here we have statistics that target the population parameter. We said there were the mean, variance, and proportions. And so we're going to talk more about that as we progress in Chapter 6. The statistics that are targeting the population parameters, they're known as unbiased estimators. So the statistics that are good, or that seem to target the population parameter, they give you good results. Those statistics are your unbiased estimators. So the mean and the variance and the proportions, those are known as unbiased estimators. All right, so are there any questions? I'm going to just stop talking for a while, give you some time to think. Are there any questions? Okay, so for the next section then, continuing chapter 6, we're going to talk about something called the central limit theorem. And I actually need to come up with, I have a simulation that I want to show you for this. And it's just a visual of what I've been talking about. And sometimes when you see the simulation, you kind of understand what I was trying to get at with the table that I just showed you. So if I could find that simulation and so that you can see what I'm talking about when I was looking at this table. And the reason that's so important is because you need to understand that in order for us to continue to section 6.5, okay? So let's go ahead and take a 5-minute break, and then when you come back at, let's see, I'll be back at 1:35. We'll go ahead and start there. All right, so those of you watching the recording, it doesn't matter for you because you can always pause if you need a break. So for you, the recording just continues. Okay? Okay, so I'm back. So starting section 6.5, I went on break because I wanted to get that that's linked to the simulation I wanted to show you. So I'm going to go ahead and show you all the definitions with the central limit theorem, very similar to what we just talked about, but it's hard to understand it just by going over the definitions. I actually wanted to show you what's happening. And so that's what this is, okay? So let me go ahead and take you to my stat lab. So what I did is under lecture notes, I went ahead and gave you the link to that simulation that I want to show you, in case you want to try it on your own later. So when you click on that, this is what you'll see. Okay, so what this shows us is the population has a normal distribution. All right, so if your population is normally distributed, that's one scenario, but you can make your population have any distribution. All right, so it's not always normal. You can make it have any distribution. So, because you really don't know what your population looks like. So that's the idea. You don't know what's happening in your population. That's what you're trying to find out with samples. So by obtaining samples, you're trying to understand what's happening in your population, but we wouldn't know anything about our population to begin with. All right, so we're going to start off assuming that our population is normally distributed. So look at this animation. I am taking a sample of size 5. Now let me go ahead and clear that. So I'm going to go ahead and take a sample of 5 from my population. So there's my sample, 1, 2, 3, 4, 5. And what is done with those 5 samples is that we calculate the mean of those 5 samples. So in the graph where you see those 5 black rectangles, that represents one sample of 5. So each rectangle is a data value. And so we take all those data values and we find the mean. We average it out. And the blue rectangle, that's the mean of your sample from above. All right, so we keep track of what that mean is. Now you do that again. You take another 5. You take another sample of 5. You take another sample of 5. And you find the average, or you find the mean. And now you keep track of it. So the blue rectangles are all the means from the different samples that we're getting. We're going to do that again. 1, 2, 3, 4, 5. There's another sample of 5 data values. So we find the mean and we keep track of it. And we keep doing that. Here's another sample, 1, 2, 3, 4, 5. And notice that when we grab a new sample of 5, there's another blue rectangle below it because that is another sample mean. Okay, so another sample, 1, 2, 3, 4, 5. That's a new sample. So we obtain the sample mean, which is a brand new blue rectangle on the bottom. Okay, so I do that more times, and you're keeping track of the sample means. And so what we're trying to do here is we're trying to pay attention to the distribution of the sample means. You're trying to look at the distribution of those blue rectangles. What is that looking like? Now the samples are pretty small, right? They're all size 5. But what if we took samples of 10,000 and calculated that sample mean? Even though our sample is size 5, look at what's happening. As soon as someone sees it and types it out, I'll stop it. So our population is normally distributed. What is happening with the distribution of our sample means? All right, so let me fast forward this. Oh no, this is pretty good, even though it's going slow. The picture's almost complete. All right, so one person guessed. It's interesting how that happens. You see that there's more in the middle. There's more blue rectangles in the middle. All right, so I'm just gonna click on. I'm getting tired of clicking here, so I'm gonna just click on 10,000. So again. Woo! So look what happens there. So yes. So it is becoming normal, right? So the distribution of sample means, it is normal. It's a normal distribution. Okay, now maybe you weren't very impressed by this because, well, the population was normally distributed. So if you take all these different samples of the same size and you look at the sample means, then those should also be normally distributed. So maybe you were not impressed by that. So let me go ahead and write down what I just did on the board. All right, so if our population is normal, which it is here, right? If our population is normal, then what we notice is that the distribution of sample means is also going to be normal. So now my horizontal axis is x bar. So remember, in the previous section, we first started with the standard normal distribution where the mean was 0, and the horizontal axis represented z. And then we looked at non-standard normal distributions, and a non-standard normal distribution where the mean was not 0. That horizontal axis was just x. So we had a standard normal distribution and non-standard normal distribution. Now we're looking at this distribution of sample means. That's what we have here. How are the sample means distributed? Okay, so your horizontal axis represents not data values, but it represents the means of all your samples. It represents the means of all your samples. And so what the previous section told us is that the mean of our population is equal to the mean of our sample means. And that is what we see in the middle. If you find the mean of all your sample means, then this is the notation we use. The mean of all your sample means happens to be the same as the mean of your population. So if you select samples of the same size and you look at their distribution, you'll see that that distribution is normal when your population is normal. Okay? All right, so I want you to take a minute to read this. All right, that's what we just did. If the original population is itself normally distributed, which it was, then the sample means will be normally distributed for any sample size. That's what we just did. Okay, now let's see what happens if our population is not normally distributed. So I'm going to take you back to the screen. All right, so I'm going to take you back to this, but now we want our distribution to be something other than normal. So maybe we can choose a skewed, maybe our population is skewed to the right. All right, so let's see what happens if our population is skewed to the right. All right, there's your first sample. So now the definition said that if our population was skewed to the right, there's a restriction on your sample size. And here my sample size is 5. So I could do this enough times and see what happens. But I was trying to show you what the definition was doing. So, or what the definition was telling us. So in order for us to get in order for the sample means to be normally distributed, your sample size had to be greater than 30. All right, so I could continue doing this, and with 5, I don't know if it'll look like a normal distribution. We can do that many times. I haven't sat here to see if it is. But what the definition tells us is that if n is greater than 30, then no matter what your parent population looks like, no matter what the population looks like, the distribution of sample means will still be normally distributed. All right, so let me go ahead and start with skewed distribution, and I'm going to take, let me do it one more time. skewed. And N, I'm going to make it, I don't know if it's going to go anywhere. So 25 is pretty close. All right. So I'm going to animate that. Okay, so now I made a 25. It doesn't give me anything greater than 25, but that should be pretty close. So it takes a sample of size 25. I wish I could get something bigger than that, but that should be pretty close. And then you keep track of what the mean is. Okay, so you keep doing that, and of course it does take time. So the next sample also has 25 data values, and all those data values are added together and divided by 25 in this case to find out the sample mean for that. So you have another sample, and you calculate the sample mean for this, for these 25 data values, and then what we do is we take note of what that sample mean is. Okay, so we do that enough times. And what we notice is that the distribution of sample means is normal. So no matter what the distribution of your population is, if you obtain many samples of the same size, when your sample is greater, when your sample size is greater than 30, you're going to see that your distribution of sample means is normal. So that's a very interesting phenomenon there, that no matter what your distribution is, so we have uniform here, if your population is uniform, but when you select samples, when you select many samples of the same size, in this case the restriction is that N has to be greater than 30, what we find is that the distribution of all those sample means is normal. All right, and that is very important. So let me move over here. All right, so what did I say before? That if our population is normally distributed, the mean of your population is equal to the mean of the sample means. If your parent population is normally distributed, then the distribution of your sample means is normally distributed. And this is true for any size N. So this is true for any size, any sample size. But when your original population is not normally distributed, then your sample size has to be greater than or equal to 30 in order for the distribution of sample means to be normally distributed. So when you look at that normal distribution, that is the distribution of your sample means, so that the mean of your population is the same as the mean of your sample means. So when your population is not normally distributed, your sample means will be normally distributed as long as you have N greater than or equal to 30. All right, so that's what this first part tells you. Now, there it says N larger than 30. So some textbooks have greater than or equal to, and this one has just greater than. So we're going to change that to greater than, just so it's the same. So greater than 30. Okay, so that's very important. So for sample of size N larger than 30, the distribution of sample means can be approximated by this normal distribution. And this is really important because remember how dependent we're getting on that shape, on that normal distribution. If you look at that table that we've been using, then you see it's a normal distribution. So I'm going to open up that table, the standard normal table, one more time. Okay, so this is what I was talking about. If you go back to this table, notice that it's for a standard normal distribution. So we're relying on the fact that we have a normal distribution. This being the standard normal distribution, we are relying on the fact that this is what our distribution looks like. So you know, in real life, populations don't always have this distribution. And so that's why that simulation that I just showed you is very important. Because now you know that no matter what the shape of your population is, when you go and select many samples of the same size, the condition being that your sample size is greater than 30, the distribution of your sample means are going to be normally distributed. So we have that distribution, that normal distribution coming back to us again. All right, so I gave you a link to that website where you get to play around with selecting samples from the population and recording the sample means. So then you get to see what happens with all those sample means. You get to see the distribution that is formed. And I had a case where the population was normally distributed, and then another case where the population was not normally distributed. So now that we know that our sample means are going to be normally distributed, we can continue using that table that we talked about the other day. We can continue using our table A2 to find areas underneath the curve. But now what we're doing is we're now looking at not an individual, but we're now looking at samples. So in the past, we've been looking for the probability that an individual, that a randomly selected individual was, that's just information about one randomly selected person. Well, now what you notice that we're now looking at the distribution of sample means. So we're now finding the probability that a sample has a mean that is greater than or less than whatever's given. So now the information that you're looking at has to do with a sample versus a randomly selected individual. Okay, so that's what I wanted to talk about. I wanted to show you those simulations first before I actually went through all the definitions. But that brings us to the central limit theorem, and that's the section 6.5. All right, so I'm going to go now back to what I have here in my definition. So we are going to be looking at a random variable x. Here, again, your random variable is continuous, and that just means that the horizontal axis represents the random variable, which is coming from, your data values come from some measurement. So continuous variable means that, or continuous random variable means that your data comes from some type of measurement. So whether talking about height or weight or distance, that's all some type of measurement. So it's a continuous random variable. So this random variable x has a distribution which may or may not be normal. The mean is mu and the standard deviation is sigma. Now this is from your population. So the distribution in our population may or may not be normal. But when you take samples of size n from that population, the samples that are selected are going to be normally distributed. All right, and I gave you those two scenarios of how that's going to happen. All right, so we're going to select simple random samples, all of size n, from the population. And these samples are selected in a way that every sample of size n has the same chance of being selected. All right, so when we obtain those samples, the distribution of x bar, which is your sample means, will approach a normal distribution. And that's what I showed you with the simulation. So x bar is the sample mean. X bar is the sample mean. Mu is the population mean. So the mean of the sample means, I gave it a different, it's a new notation. The mean of the sample means, oops, that did not circle it very well. Let me try it again. This is the notation for the mean of the sample means. So the mean of the sample means is the population mean. So using symbols, that's what I'm talking about. Now the standard deviation of all sample means, this is the symbol for it. The standard deviation of the sample means is equal to the population standard deviation over the square root of n. That's what you see here. Okay, so these are two very, very important parts to remember. I am putting a box around them. Very important to remember this. All right? Okay, and here it is again. The mean of the sample means, the standard deviation of the sample means. It's also called the standard error of the mean. So we're talking now about samples, the distribution of samples. So here is just this is the population that's uniform. The distribution is uniform. But if we randomly select many samples of the same size, where remember you have to make sure they're greater than 30, the distribution of those sample means will have a normal distribution. So here, 500,000 random digits were generated, and they were grouped into 5,000 samples of 100 each. So that meets the requirement where it's greater than 30. 100 is greater than 30, so it works. So if we find the mean of each sample, we will find that the distribution of sample means will be normally distributed. All right, so the distribution of sample means, now we're talking about x bar as our horizontal axis. So they're going to be normally distributed. All right, so I already showed you that. I've already showed you the simulation for that. Okay, so as far as doing the homework in this section, there's one thing that's going to make this section different than what we've done before. And so that's what I'm going to show you next. How does this actually change what you've been doing? So the first part of my example, this is what we've been doing in the past. And then the next part of my example, that's what we're now doing with the central limit theorem. So I'm going to show you the difference, okay? All right, so before the central limit theorem, this is how the questions were phrased. So given a population of men, we have normally distributed weights. And the mean is 172 pounds with a standard deviation of 29. If one man is randomly selected, okay, so one person being randomly selected, find the probability that the weight is greater than 175 pounds. So in the past, when we know that it's normally distributed, we draw a normal curve. The mean is 175, so that goes in the middle. Now, it's not a standard normal distribution. It's a non-standard normal distribution. So I have to compare that to a standard normal distribution. And I do that by drawing out my horizontal axis here. That is now representative of Z. The mean for a standard normal distribution is 0. Okay, now here's the question. If one man is randomly selected, find the probability that his weight is greater than 175. Okay, so I just put 175 there, but the mean is not 175. I misread that. The mean was 172. All right, so that's what it says up here. The mean is 172. The question was to find the probability that the weight is greater than 175. So 175 is located to the right of the mean. So 175. So we want to find the area that is to the right of 175. So the probability that the weight is greater than 175 pounds. So I'm trying to find the area to the right of 175. And the mean, again, is in the middle, but the mean that was given to me was 172. So I had to correct that. All right, so we need to find this area. I can't do that unless I know the z-score. Because remember, if I'm going to use table A2, I need a z-score. So I need to standardize this. So I'm going to put a question mark here. What z-score represents 175? We had a formula for that, right? So z is equal to x minus the mean divided by the standard deviation. That was our conversion formula to find z. So in this case, x is our 175. The mean was given to us, and the standard deviation was as well. So that's how you're going to find your z-score. You have parentheses in the numerator to keep it together. So let me know what z-score you get. Okay, so if you didn't get 0.10, because remember z-scores are rounded to 2 places, then you want to make sure you verify your calculation, make sure you put parentheses in the numerator. But yes, z-scores are rounded to 2 places after the decimal. So the 0.103 that you're giving me there, I'm going to put as 0.10. All right, so z-scores are rounded to 2 places, and this right here was the z-score that we were finding. Okay, so now that I have a z-score, I can use table A2. So you're going to look up the z-score of 0.10. And 0.10 is a positive number. So remember, 0.10 is a z-score. So when you look it up, what do you get for the area? All right, so 0.10, here's 0.1, and 0 is over here. So if your z-score is 0.10, remember it's a z-score, so you have to be on the leftmost column. So you guys typed out 0.5395. That's really tiny. I can't see it. But I see 0.5398. 0.5398. All right, so do you still see white? It just takes a little bit of time for it to transfer over. So I think my writing comes on there before the actual picture. So you should be able to see it now. So what I did is I just copied the table over. So if you can't see what I'm writing on, just go ahead and look at your table, and it's table A2, positive z-scores. And if you look up 0.1, you're going to end up with 0.5398. Do you see it now? All right. So again, if you can't see it, it's on your table. Sometimes it takes a while for it to transfer over. So 0.109, it's 0.5398. So I am pointing to the area. Okay, so then we know what our area, now that's an area, but remember it's always the area to the left of the z-score you were looking up. And I don't think that's what we wanted. I needed the area to the right, not the area to the left. But the way the table works is when you look up a z-score, you're always going to get the area to the left. So that was 0.5398. But that's not our answer in this case. So remember how we get the right area. If we have the left area, we get the right area. Yes, by subtracting 0.5398, subtracting that from 1. Yes? Okay. So we end up with the right, which is, let me write it down first, 1 minus 0.5398, and you got 0.4602. 0.4602. And that's our probability. Now that's the probability for one individual. Right? That's the probability for an individual. All right, so I just noticed that when I did that, okay, my tools keep going somewhere, and I can't. Okay, I found it here. Every time I write a decimal, it moves up. It looks like it's a minus. It's a decimal. There it is. Okay, so that is the probability that, and if one man is randomly selected, that's the probability that he's going to weigh greater than 175 pounds. Again, this is assuming we have a normal distribution. So 0.4602, that's almost, 50-50, right? That's almost at 0.5. That's almost a 50-50 chance that if a man is randomly selected, he's going to weigh more than 175 pounds. Okay, so that's how we did the problems before. Now with the central limit theorem, let me go ahead and show you how we would do how we would do a similar problem. Okay, so look at how the question is now phrased. Given a population of men, we know that weights are normally distributed. The mean is 172. The standard deviation is 29. That hasn't changed. That's the same. If 20 different men are randomly selected, okay, now it's not one randomly selected man, now it's 20 men. So you're given a sample size. So with the central limit theorem, you're going to be given a sample size. If 20 different men are randomly selected, find the probability that their mean weight, so now it is the probability that their mean weight, that's the probability of X bar, that their mean weight is greater than 175. So look at how that was different from before. Before, I wrote the probability that X was greater than 175. Not X bar, but X. Because when we're looking at that distribution, that is your distribution of X, of your actual data values. But now we are looking at the distribution of their sample means. So when you draw your curve, now we're looking at the distribution of sample means. So when you write down the probability that their mean weight is greater than 175, you have to use X bar for the mean weight. Okay, so labeling this is very similar. We have 172 for the mean. 175 is to the right. And the region that we're shading is the same region. But keep in mind that now we're looking at the distribution of sample means. So shading everything to the right, that's still the same. Now, I don't have a standard normal distribution here, so I need to draw my horizontal scale so that it represents a standard normal distribution. So that means I need to find the z-score that corresponds to the 175. So the formula for the z-score changes. Before, the formula looked like this. Z equals X minus the mean divided by the standard deviation. That's what it was before. Now the formula is going to look like this. Now it's going to be not X, but it's going to be X bar because it's the distribution of our sample means. So it's X bar minus the mean of our sample means divided by the standard deviation of our sample means. Now, you remember that, hopefully, that the mean of your sample means is equal to the mean of the population. And you hopefully also remember that the standard deviation of your sample means is equal to the standard deviation of your population divided by the square root of n. So you can just make those replacements. You can just go ahead and substitute that in. So instead of writing X bar, you can just write mu. And instead of writing sigma with X bar, you can write the equivalent form of it. Okay, so this is what your formula looks like. I'm going to write it at the bottom here. You're going to write Z equals X bar minus the mean of your sample means, which is the same thing as the mean of your population, divided by the standard deviation over the square root of n. So that becomes the new formula for figuring out what Z is. So that's how it's different from what we were doing before as far as the calculation is concerned. When you do use this formula, make sure you put parentheses in the numerator and parentheses in the denominator so everything stays together. So whatever's supposed to be in the numerator stays in the numerator, whatever's in the denominator stays in the denominator. Okay, so now I am going to plug everything in that I have. So we have X bar, which is 175. That's what we have on the horizontal axis. minus the mean of my population divided by the standard deviation over the square root of my sample size, which is 20. That's our n. So if you just look at that part of figuring out z, look at how it's different from before. It looks very similar, except that the denominator is now being divided by the square root of n. All right, so this bottom part of your denominator is you have that square root of 20. All right, so that's going to give you your new z-score. So go ahead and type that into your calculator and tell me what you get. Remember, z-scores are rounded to 2 places. Okay, so you guys are getting 0.46. Okay, so z is equal to 0.46. 0.46. Okay, if you're not getting that, I'm going to show you on the calculator how you can get it, okay? But for right now, because we are getting close to ending, I'm going to go ahead and put 0.46 down here. 0.46. So if you're not getting 0.46, stay tuned. I'm going to show you on the calculator how we got that. Rounded to 2 places. So 0.46 is our z-score. So when you have your z-score, you can just go to your table. Look up 0.46 on your table. 0.46. Now, of course, 0.46, that's going to give you the area to the left, right? So 0.46, here's 0.4. So 0.46, 0.40, for 1, for 2, for 3, for 4, for 5, for 6. All right, so 0.46, if you look that up, do you all agree that 0.6772 is the area to the left? 0.6, I lost it, 0.6772. 0.6772. So you look up a z-score of 0.46, and that's what you get, 0.6772. Is everybody okay with that? Okay. So that's what the area to the left is. Not the area to the right, but the area to the left. So 0.6772. Of course, that's not our answer. Remember, to find the area to the right, we have to subtract from 1. So if we do 1 minus 0.6772, that's the area to the right. Okay, so 0.3228. So here it's the probability that when 20 different men are randomly selected, the probability that their mean weight is more than 175 is 0.3228. So we're talking about a group. We're talking about a group. So the probability that sample's mean is greater than 175 is 0.3228. Okay? All right, so I'm going to print the participants list so I know who's attending. All right, if you were not able to get that z-score that we have, then please stay logged on. I'm going to show you how I got that on the calculator. I believe, though, that is the end of section 6.5. So 0.46 is what we ended up getting, and so 0.3228 was our new probability, right, for part B. So it is much easier for an individual to deviate from the mean. It's much easier for an individual to deviate from the mean than it is for a group of 20 to deviate from the mean. That's what we're looking at here. So it's much easier for an individual to deviate from the mean than it is for a group of 20 to deviate from the mean. Right, so those are our final answers for both Part A and Part B. And that's where I'm going to stop. Okay, so let me go ahead. For those of you who couldn't get that z-score on the calculator, let me show you how you would do that. All right, so I'm just going to enter this in. If you were able to get 0.46, then you're done. This is just for those who couldn't get that on their calculator. All right, so I'm entering the z-score. Okay, I'm entering the what I was trying to put in the calculator to get the z-score. So I think we had 175. Notice that I put a parentheses there, 175 minus 172. In parentheses, that's the numerator, and then you divide it by what's in the denominator. So we had a fraction in the denominator. So that was our standard deviation, which is 29, over the square root of 20. Now in the older calculators, you need parentheses in your square root, so just make sure you keep track of how many parentheses you have. You're going to need a parentheses to close your square root and another parentheses for the denominator. Here, I don't need that, so it's just the square root of 20, and I just have to make sure the denominator is in parentheses. And then that's how I got the 0.46. Z-scores are rounded to 2 places. Okay, so that's where I will stop today, and we'll continue our next lecture with Chapter 6. Don't forget to go back to the homework and look for the lecture assignment so that you can get credit for watching this lecture. All right, so I'll talk to you next time.